Okay, so as in the last video we have derived the formula for finding the velocity of the projection of a particle which is moving along the uniform circular path, right? We derived the formula. We initially took the component, the y component of the tangential velocity, and made it equal to the particles, not particle, however, shadow's velocity. And then we just simplified it. We substituted the values of the sine theta, we substituted the value of tangential velocity in it, and we simplified, and at the end we got our final formula as omega radical x naught square minus x square, which was our final formula, right? In today's video we are going to see the maximum velocity and the minimum velocity. So what we are going to study today is the maximum velocity, the maximum velocity and the minimum velocity. The minimum velocity. Now see where we're gonna have our maximum velocity. We're gonna have our maximum velocity at mean position. At mean position we're gonna have our maximum velocity. At mean position we're gonna have our maximum velocity. Now see, at mean position we know that our displacement would equal to 0. Our displacement would be equal to 0 at the mean position, right? Since we are talking about the maximum velocity, and we're gonna find our maximum velocity at the mean position, and since we know that at mean position our displacement is equal to 0, right? So x is equal to 0. Now see, what we got, our final formula was vq is equal to omega radical x naught square minus x square. Let's write the same formula here again. vq is equal to omega radical x naught square minus x square. This was our final formula, right, which we are going to use. Now see, as we have already stated that our displacement is equal to 0 since we are at our mean position, because we can find the maximum velocity at the mean position. So since we are at mean position, that's why our displacement is equal to 0. So let's substitute the x value in the formula. So let's do it. So vq is equal to omega radical x naught square minus x square, and now instead of x square I can write 0 square, and 0 square would be equal to 0, right? Now see, vq is equal to omega radical x naught square minus 0 would be x naught square. Now see, this square would be cancelled with this radical, and what we're gonna have finally, vq is equal to omega x naught. And what does x naught represent here? What does x naught represent here? An amplitude or maximum displacement right? So what is now the formula for finding the maximum velocity? Omega x naught, where x naught represents an amplitude or the maximum displacement, right? Now we have got our formula for finding the maximum velocity as well, and that is equal to omega x naught. Omega x naught. Now let's see what would be the minimum velocity, and where we're gonna find the minimum velocity. See, at mean position we had our maximum velocity, which means at extreme position now, at extreme position we're gonna find our minimum velocity, right? Where we were having our maximum displacement, we were having our maximum displacement at extreme position, and we were having minimum displacement at mean position. But here we have vice versa, since we are talking about velocity. So at mean position we'll have our maximum velocity, and at extreme position we're gonna have our minimum velocity, right? Now since we are talking about extreme position here, so our x would be equal to r, right? That we know too. Our x was equal to r. At mean position our x was equal to 0, but at you know what, extreme position our x is equal to r, or you can say x is equal to x naught, where x naught represents the maximum displacement, right? Now let's use this formula again. Let's use this formula again. What we have, minimum velocity, right, is equal to, formula is omega radical x naught square minus x square. This is our formula, which we will be of course using here, Now see, we have already written here, we have made x equal to x naught, since our projection is at extreme position now. So at extreme position we have our maximum displacement, and if we have our maximum displacement, that is of course equal to amplitude, right? So we have represented x with x naught, since it is at extreme position. Now let's substitute the values. V q minimum is equal to same omega, right, x naught square. Instead of x, now we are putting x naught, right, and square. Let me mention this here. We have made x equal to x naught. We have made x equal to x naught, right? Now see, VQ minimum is equal to omega. Now see, x naught minus x naught is 0, and 0 multiplied by omega would be 0, right? So VQ minimum is actually equal to 0. So the velocity, the minimum velocity is equal to 0. Where we're gonna find it? We're gonna find this minimum velocity 0 at extreme position. At mean position we're gonna find our maximum velocity, and at extreme position we're gonna find our minimum velocity. The maximum velocity we found since we made x equal to 0, since at mean position the displacement is minimum, which is 0. So we substituted the value of x as 0 in the formula omega radical x naught square minus x square, and finally we got our formula for finding the maximum velocity at mean position is VQ maximum is equal to omega x naught, right, where x naught represents amplitude or the maximum displacement. Then we found the formula for finding the minimum velocity, and the minimum velocity we're gonna find at extreme position. At extreme position our x would be equal to the radius of the circle, or our x would be equal to x naught, where x naught represents the maximum displacement, right? So V minimum is equal to omega radical we have just substituted the value of x as x naught. So x naught square minus x naught square, we got 0, right? So radical 0 is 0 and 0 multiplied with omega is 0. So our minimum velocity is 0 and maximum velocity is omega x naught. In the next video we're gonna find we're gonna derive the formula for finding the acceleration of the projection of a particle which will gonna move along the circular path.